So this is the 8th question of CodeChef Starter 119 Division 4. Guess who delivers? In this question, there are basically two pizza delivery guys, and there is a tree consisting of n nodes and n-1 edges. And these two drivers can basically start at any point at the beginning of the first day, and they need not start on the same nodes, right?
Yeah.
There are m days, and on each of the m days, uh, there 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 has to be a delivery made from the node Si to the node Di. So as mentioned here, from node Si to Di on the ith day, and any one of the delivery guys has to make that delivery.
Yeah.
Now, while traveling from source to destination, there is one more constraint that for every edge they travel, it will require them 2 units of time to
Right.
travel that edge. But if they
Yeah.
travel the same edge twice, same edge for the second time, then they don't need 2 units of time. They only need 1 unit of time in that case.
Yeah.
So we just basically need to find the total number of the minimum total time required to deliver all the pizzas. Okay, and
Yeah.
this 1 unit of time will apply only for the same day. So if the day is over, then it will reset. So on the same day, if he's traveling the same edge on the same day, only then it will be reduced to 1 unit. Okay,
Yeah.
about the question, and the constraints are the n value, the number of nodes in the tree, can be up to 5,000. The m
Yeah.
values, the number of days, can be up to 5,000. And the source, destination, and the vertex values will obviously be in the range 1 to n. Okay.
Yeah.
And they've also mentioned that the sum of n and m over all test cases won't exceed 5,000.
Yeah.
And test cases are also 100. Okay. So yeah, let's see how we can solve this question.
Yeah. So, for this question, firstly, the prerequisites are you should know DFS and dynamic programming. Right. So now, let us define few terms here. Firstly, it is distance of I of j, right? This is distance of I of j denotes what is the distance in the tree. We know that we are given a tree, and tree will always have n-1 vertices, right?
Right.
And there won't be any cycle in the tree. So now distance of I of j defines what is the distance between what is the distance between I to j, node I to j, right? So here, if we look at the constraints, constraints are just 5,000, right? I mean, number of nodes can just be till 5,000 in the
Only
verse.
till 5,000. Right.
So because it's 5,000, what we can do is we can fix a node and do a DFS and find this distance out. So whatever distance we are finding, that is the shortest distance. So this will denote as what is the shortest distance between I to j, right?
Right. Yeah.
So for that, fix I to calculate this, just fix I and then do a DFS.
Right.
So by doing this, we'll get distance from I to every node. Now fix
Mhm.
some other node and then calculate the distance. Similarly,
So
fix each and every node.
basically, for
Yeah,
every node, we fix that node and do a DFS and
yeah,
find the distance to all other nodes, right?
yeah, to all other nodes.
Like a pre-computation.
Yeah, like a pre-computation. So
Okay.
from
Yeah.
1 to n, fix ith node, do a DFS and find the distance to
Okay. Got it.
every other node j. So
Right.
that's what distance of ij denotes. Now comes the DP part. Right? So in DP, we have it's a 2D DP. So DP of I and node. This is what we have. Now what this denotes is, it will denote that we are currently on the ith day. ith day, right? And one of the person is on node node, right? So basically we are on the ith day, and one of the person is on the node, and the other person is on the node destination -1, right? So basically we are currently on the ith day, and there are two people. So we don't consider which person is on uh, node, but we are assuming that among these two people, one of the person is on node, and we know the other person will definitely be at destination -1, right? Destination of I -1, right?
Destination of I minus 1.
Yeah,
Yeah, right. That is true.
because like for sure one of the person should have delivered the previous one,
Uh,
like
in the
should have
previous
delivered the
iteration,
previous.
he will have delivered the pizza, right?
Yeah.
So
In the
yeah,
previous day,
that is true.
he should have delivered the pizza, and one more person might have delivered on some day which is lesser than the previous day. Okay?
Right, yeah,
And that and we are basically tracking the person who delivered pizza, which is lesser than the I -1th day. So we are basically tracking on which node the person who delivered the pizza uh, with the day lesser than I -1 is currently on. Right? That is
right,
what
yeah.
this did.
Mm-hmm.
And other person we need not maintain a state. Why? Because from I itself we know where will he be. He'll be on d of I -1, right? Because he should have delivered the I -1 day's pizza.
Yeah, exactly.
So the definition is we are currently on the ith day, and one of the person is on node, and other person is on node destination of I -1, right? Let's call D as destination. So
Yeah,
here
right,
itself, let's define two more things. S means source, given source, all set of sources,
right.
and D means all set of destinations.
Yeah,
Okay? Now, this is our DP definition, right? So let's see how we can make transitions for these. So uh, now the DP size would be DP of N and M, right? Before going into the transitions, DP of size will be DP of N of M, right? Sorry, not N of M, it would be M of N, because M represents number of days, right? And N represents the node
number of
numbers,
nodes. Yeah,
number of nodes. So yeah, for now, let's maintain N plus 1. Let's consider nodes as 1 based indexed, and days as 0 based indexed, right? So this is our DP size, and this is how we define. Now let's
right,
see the transitions for DP. So now let us assume that we are using DP as a DP to memorize our answers, right? And then let's figure out the transitions with respect to a recursive function. So now, uh, what all type of states can we have? So initially, we call, let's say solve is the function, recursive function. So initially we need to call solve it. Basically solve will take two parameters, that is I and node. This is what it takes, right? And we are using DP to memorize the values of solve, right?
Right. Yeah.
So now, uh, now initially, can we say that solve will be 1 comma x of I plus 2 into distance between x of 0 of y of 0, right?
Yeah. That is right.
So this just means the first person have,
Hmm.
we don't know which person, like we are not fixing the order of the people, but among those two people, some person have delivered the first order and the other person is on xith node, is what we are assuming, right?
Yeah.
Because we can see that it is useless for a person to start off with a node apart from source of some delivery, right? Some pizza delivery.
Right. Yeah.
Because if he starts with a node which is not a source of pizza delivery, then he need to
Hmm.
travel little extra. So
Right.
if we
Exactly.
really see, that is useless, right?
Hmm.
So now that is why we are assuming one person will always be at some source
Okay. Hmm.
of the pizza, and the first person uh, and other person will always deliver the first pizza, right? So this will be the start of. So initially we can
So
try all possibilities.
can we
So
also say that the
yeah,
other person will be on the source of the second uh, day, or
um,
will it not be
no, he'll
optimal?
basically be on the destination of the second. I mean, destination of the first day.
Okay. Okay.
Like basically, before we start, we can say
Hmm.
that first person will be on the source of the first day.
Yeah.
I mean, one person will be on the source of the first day, and other
Yeah.
person will be on the source of some other day.
Okay. Okay. Yeah. It doesn't have to be second day necessarily. Any other
Yeah,
days also.
yeah. Any other day is also fine.
Okay. Hmm.
So here first person is we assume first person was on the source of the first day, and he delivered the pizza of the first day. So this is because he delivered the pizza. So this is the value that we got.
Yeah. Got it.
And second person, we are assuming that he's at some source x of I, right?
Right.
And I can vary from 1 to m minus 1, right? Considering zero based, because zero is
Hmm.
already done. So, and
Yeah.
one more thing, it's useless for two people to be on the same node also, right?
Yeah. That is true.
So that is why we assume this is the scenario. Like
Hmm.
initially starting with the same node is useless. So that is why we don't consider I as zero.
Right. Yeah.
So now let's see the transitions. Now solve of I, for any solve of I of node, let's see how we can make the transitions. So I represents uh, like we finished I days and we are currently on the ith day, and uh, the and one of the person is on destination I minus 1, right? And the other person is on the node. So now there can exist two scenarios: ith days delivery. First case is ith days pizza delivery. could be done by a person on node, right? So first case is uh, ith days pizza delivery could be done by the person who is on. Okay, let's consider ith days delivery. Pizza delivery could be done by the person who is on destination of I minus one, right?
Yeah.
This is because we are on the ith day and we know one person is on destination of the previous day and the other person is on some node, right?
Right. Right.
And
Yeah.
that node we already have track of.
Yeah.
So now let's see how we can calculate this. Let us now, can we say that the transition for this will look like solve. So now next we'll be going to the next day, right?
Yeah.
So ith days delivery is done by the person who is on d of I minus one, and the other person will still remain on node, right?
Right.
So one of the transition is solve of I plus one comma node plus, this is one of the possibility. Let's call it as first value, plus let me call it as uh, the travel time, plus the travel time. Travel time represents the time taken for the person who is on destination of I minus one to go to source, and then from source go to the destination, right? Like he's basically going to S of I and then going to D of I from S of I.
Yeah. Mm.
So this is one transition. And the next choice is on the ith day. Basically, ith day is pizza. Delivery could be done by person on node, right? Person on node, right? These are the two scenarios. So in this scenario, how will our transition look like? So can we say our transition is solve of, we are moving to the next day, which is I plus one, comma, and we are making the person who is on node to basically pick the current pizza, right?
Yeah.
So that means the other person is on the node which is at the previous day's destination, right?
Right. Yeah.
So it would be solve of I plus one the next day, comma the other person's endpoint, basically where the other person is. So the other person is at destination of I minus one plus the travel time that the second person took, right? So by second person, I mean the person who is on node took, right? Uh,
Right.
Node represents the variable.
Yeah.
Node
Yeah.
variable passed to the solve
Mm-hmm.
plus the travel time, right?
Right.
So can we say that dp of I of node? So the value of dp of I of node, that is reaching I days from I days to node. Let's say we reached ith day with a parameter node, and from now
Okay.
if we recursively explore and find the answer, then the best answer that we got is either v1 or v2, right? Because we want to
Right.
minimize our time, we'll
Mm-hmm.
pick the minimum one among among both the choices.
Yeah.
So this will be our dp. So this is how we can make the transitions, right?
Right.
But now the thing is, how do we calculate the travel time? So this is the travel time taken by person who is on d of I minus one, right?
Okay.
And
Mm.
this is the travel time taken by person who is on node.
Right.
So now let's see how we can find this travel time. So now to find the travel time, let's consider a tree. So now I'm not numbering the tree. Like to calculate the travel time, we just need the tree structure
Yeah,
with
that's right.
probability. So let's say this is how the tree is, right?
Okay. Hmm.
So I didn't assume that this is some subpart of a tree, which we only include the nodes that we need to travel.
Right,
So
right.
that means from the tree we just took out the nodes where the person is. So red colored node is the point where the person is, and this is the source, and this is the destination, right?
Yeah,
So now this person should first come to source and then go back to this point and then go to destination, right?
right.
So if we manually see, the time taken by this person would be 2 units for this edge, 2 units for this edge,
Yeah,
2 units for this, two for this, two for this, two for this, and here 3 units, 3 units, 3 units, right? Because he's coming, going back, and then going like this.
right, right. Yeah,
So when as per the question, when he visits the edge for the second time, he'll only take 1 unit, right?
yeah.
So now our aim is to find out the sum of this. That is what the travel time is, right? Sum of these values.
Right.
Sum of number of times each edge we visited in the shortest path between the three nodes.
Yeah, that is right.
So now for that, let us define few things. Let us call this distance as d2, right? Let us call this distance as d1, and let us call this distance as d3, right? And now, how can we get these distances firstly? Can I say d1 is nothing but, so I'm just naming these nodes with x, y, z.
So
This is
basically
x,
the
this is y,
distance we
this is z.
computed previously.
Yeah. So we can get it by the distance that we computed previously, right?
Yeah,
So let's say
distance of
x, y,
X and
and z
Y.
are the nodes.
Hmm.
Then d1 is distance of x to y, d2 is distance of y to z, and d3 is distance of x to z, right?
Yeah.
These are the three things, let's say. Now let's
Hmm.
calculate the travel time. So now firstly, let's say I added d1 plus d2, 2 into
Okay.
d1 plus d2, right?
Right.
This just means that we added 2 to this, 2 to this, right? Then
Right.
we
Right.
added
Right.
2 to this, 2 to this, 2 to this, 2 to this, and we added 4 to these things, right? If we see
Yeah. Exactly.
by
Hmm.
doing this. Now
Right.
we want to remove one from all these nodes, right?
Right. Yeah.
So to remove one from all these nodes, uh, we should subtract this path only, right?
Exactly. Hmm.
So to get that path, uh, let's say we did d1 plus d2, then
Okay.
we can observe that we included this one and we included this one, right?
Right.
So when we included these two, this path is included twice, right?
Twice. Right.
And this path is included once.
Hmm. So we
And
can do
this path
minus
is nothing
D3.
but, yeah, this path is nothing but d3.
Hmm.
So we'll do minus d3,
And by 2.
yeah, minus d3. And now after subtracting d3, we know this path is included twice, but we should only
Hmm.
subtract it once. So we'll do by d2
Hmm.
divided by d. And this will always be divisible by 2
Right.
because we are including a part twice. So that will
Exactly.
always be a multiple of.
Right. Right. Right.
So this way we can calculate travel time between the source, I mean between the starting node where the person is. So here, uh, yeah. So here starting node of the person is nothing but x, So if in
Okay.
case we want to compute this travel time, we
Mm.
can just compute it like this, right? Where
Yeah,
we
yeah,
can,
exactly.
where here x is the starting time, x is the starting node of the person,
Okay.
not starting node. Let's say x is the node
Mm.
where the person is,
Yeah,
where the person is. Y is the node, y is the source where the person need to go on the ith day, and z is the destination where the person need to go in the ith day, right?
right. Yeah,
So with these definitions, we could compute the travel time as this thing which we derived. So we can apply the same thing as per the uh, identifying the x, y, and z values from this, right? From these
right,
transitions and calculate the travel time. So now, so this way we can solve the problem. So
right.
now it's all just pre-compute as a just pre-compute distance values, distance of ij
Mm.
by doing a brute force and then running by fixing I and doing DFS and then calculating the I to j shortest distances.
Right, right. Yeah,
Now we just define the DP. So now we can uh, yeah, we can just make a call to solve 1 comma x of I plus 2 into distance of x of 0 y of 0, right? And
right.
here make a call for every varying xi, right?
Exactly. Mm.
And here in the solve, this way we can make the transitions as discussed. First
Right,
one represents if the ith on the ith day, if the person who is on d of I minus 1 node uh, picks the ith pizza, and v2 represents on the ith day if the person who is on node picks the pizza. So out of these two choices, minimum is the value. And now this
right.
DP will use
Yes.
as a will use as a memory source for solve function. So
Okay,
in
okay.
case, let's say if
Mm.
DP of I of node is already computed, this is computed.
Right.
So we can maintain some kind of variable to detect that.
Yeah,
We
we
can
can store
maintain
it
some
as
invalid
-1 or
value.
something.
Yeah, we can store it as any invalid value to check if it's computed or not. If
Mm.
it's computed, then instead of recomputing, just return it.
Yeah, yeah. That's how DP usually works, right?
Yeah.
Yes.
So uh, so because we are just memorizing them, uh, the number of though the transitions look like 2 power, though the transitions look like exponent, they are
Mm.
not actually exponent. So
Right, right.
number of transitions will be n into m only, right? Because DP
Yeah,
size is n into m. It's n plus 1 into m.
right,
As DP size is n plus 1 into m. And we are in the worst case we'll memorize every state in DP.
right. So what
So
will be the time complexity of this approach?
yeah, so if we look at the time complexity of this is big of n plus 1 into m, right? N plus 1 into m plus again n into n plus, we can say n into n. Okay?
Right, yeah.
This n into n because we'll be doing a DFS to pre-compute distance, right?
Pre-compute distance, right, yeah.
And now if we look at the space complexity will be big of n plus 1, and this can be made n also because we considered nodes as 1 based. This is n plus 1.
Yeah,
You
yeah,
can even make 0 based because we are never
yeah,
using zeros,
exactly.
right?
Right, right, right.
So, so just to write it in an optimized way, let's say we made it 0 based states, then it would be n into m here, time complexity, and here it would be space would be n into m plus n into n, right?
And into it. Yeah,
So now here the space is fine according to the given limit, but
yeah,
space can further be optimized. That is, whatever transitions we see here, right? we did this recursively, right?
Right.
So same transitions can be applied iteratively also, right?
Okay.
So our base would be dp of 1 of x of I will be
Okay.
equal to 2 into distance of x of 0 and y of 0. And then
Mm-hmm.
we can just look over these recursive transitions and make the iterative transitions out of the recursion, right?
Yeah. Yeah.
So now
So yeah, if we
here,
do it iteratively, we can optimize the space as
yeah,
well.
we can optimize the space as well. Like if we do iteratively, we can do iteratively with n into m plus n into n space. And one more observation to optimize this memory is if we see in the solve, every I depends on the next state only, right? Only on
Yeah.
I plus 1. But when
Right.
we are at ith node, we don't need the memorized values of I plus 2, I plus 3, I plus 4, and so on. Right?
Right. Yeah.
So because of this, what we can do is while we can just implement the same thing iteratively and maintain only two DPs, DP1, DP2, right?
Yeah.
So DP1 will store what, let's say we are making the transitions with respect to I and I minus 1, right? Let's say this is how we are making the iterative transitions, I and I minus 1.
Mm-hmm.
Now, when we are at I, we know till I minus 1, we already computed the values, right? Till I minus 1
Right.
day, we already have the values.
Right. Yeah.
Then, uh, then if we look over the transitions, then if we look over the transitions, it just means that we only need to know what is I, what is the value of, what is any value of I minus 1 to find out any transition of dp of I, right?
Yeah.
So, so like considering a scenario where we are
So
on the,
basically,
yeah,
based on dp of I minus one values, we compute dp of I value, right?
yeah, we compute dp of I value.
And then we don't need the I minus one anymore for
Yeah,
computing I plus one.
yeah,
So we can just override all the values of I minus one with I plus one values and keep switching, right?
yeah, keep switching.
Mm.
So, like considering a scenario where we are calculating the values for dp of I, and we already calculated the values of dp of I minus 1.
Yeah.
dp of 1 will tell us the i's values, all the i's dp of I values, and
Right.
dp of 2 tells us all the I minus 1's values. Right?
Right.
So with this, we can just maintain dp, two dp values, and the dp size, dp1 size will be n, right?
Hmm.
And dp2 size will be n.
Yeah.
So in our case, it is n plus 1 because we are doing it 1 based,
Yeah.
but this 1 can be optimized by doing it 0 based.
Yeah.
So, and one more thing is uh, we optimize this to n right now, but we
Right.
need to optimize this also because n into n also would give us more memory.
Right.
So it is sufficient. So to optimize this, what we can do is we can observe that when we are at I plus 1, so here if we look at the dependencies
Hmm.
to calculate travel time, we only use distance to calculate travel time, right?
Yeah.
So when we are at ith node,
Okay.
we have source of I and destination of I, right?
Right.
So it is sufficient to find out all distances from source of I to all other nodes and all distances from
Hmm.
destination of I to all other nodes, right? If we have those two uh, things, let's call distance 1 as distance from source of I to all
Right.
other
Yeah.
nodes, and distance
Hmm.
2 of distance 2 as uh, destination of I to all other nodes.
Right.
And obviously the size of this will be n as we are computing for all the nodes. So it would be n plus 1 in this case as we are computing it 1 based.
Right. Yeah.
So, and if it's 0 based, we can remove the 1 depending on the way we implement. And
Yeah.
now
Hmm.
we can just make a DFS call, find out all the distances from S of I. and all the distances from D of I, right? So here, instead of pre-calculating everything, when we are at I, we can just calculate the distance for two values, right? And we don't care about the distances of other values when we are at ith. I mean, when we are at ith day, right?
Right.
So
Yeah.
because we don't care about that, instead of pre-calculating distance and maintaining it as a 2D array, we can
Yeah.
just reduce it down to a 1D array.
Yeah.
So
Exactly.
now the time complexity, if we see,
Time complexity will remain the same almost, right?
n into n
Only
and n into n.
space
Space
will be
complexity
improved.
will be big of n plus n, right? In the
Right.
worst
Yeah.
case.
Mm-hmm.
So
Right.
this way we can solve the problem. This is
Okay.
per test case,
Right.
and we can see in the constraints that if we
Sum
look
of
at the
n
dependency,
plus m value overall test cases is
yeah.
not more than 5,000.
So
So this
summation of
will,
n and m is less than or equal to 5,000.
right. Yeah.
We can assume there is one test case only with n and m as
Yeah.
5,000 perfect, and
Mm-hmm.
that can be the worst scenario. And this
Right.
time complexity is sufficient enough for the given TL, and space is sufficient enough for the given memory unit. So here,
Right. Right.
though we could have done it with this space, it would have still gotten accepted as a
Okay.
memory
Mm-hmm.
limit of n into m plus n into n is also allowed in the question. And in case
Okay.
if you want to optimize the memory, then this is how we can optimize. And this will for sure work as it's two optimized memory.
Right.
So this is
Exactly.
sufficient enough to pass the memory limit.
Right. Yeah.
So
I
this
think
way
this
we
is
can
clear,
solve the
Shishma.
problem.